visualization aspects of our seamless astronomy program here. But I want to put them in the context of not just, how do you make beautiful pictures that attract attention, but instead, how do you use visualization to actually understand the information that you've gathered and that you're trying very hard to get some kind of physical insight from. And this title slide gives you a sense of the kinds of topics I will cover. And for some of you, I would imagine that those logos and little icons are familiar, but for others of you, they're not. My goal is that by the end of the talk, they will be. And for anybody who wants to just take out your phone, take this little picture here, you can get the handout digitally, which is in the back of the room, that has a list of many, many links to many useful websites and tools that I'm going to mention in the talk. And I'll show that again at the end. Now, before I get started, I have to explain that in addition to the Seamless Astronomy group here that Gus mentioned, there are many particularly key members of that group and also outside collaborators who are pictured right here. And so some of these people are in the room, notably Chris Beaumont, who's over there. I can't see in the dark. Maybe Nathan is here. Maybe Elizabeth Newton, I can't see. Anyway, these are people well known to you, and their contributions will come up during the talk. Okay, so now let me actually get started. And I've shown this slide many times, and it's probably the most important thing to appreciate from the talk, which is that some people have an impression of visualization as something that would be unnecessary if only we could make computers smart enough. And that may be true, but the important point is that computers are nowhere near smart enough, okay? And smart enough is defined as smart as us, okay? And so what humans have evolved to do is recognize patterns very quickly, okay? Astronomy results are unlikely to be chasing you and trying to kill you, but the same cognitive systems in your brain that let you very quickly, pick out a cheetah running at you in the grass, let you pick out a bubble in the interstellar medium, okay? So we are better at this than computers. Computers, on the other hand, are tremendously better than us at making very large, complicated calculations. And I'll show you later some examples where you really leverage these two things off each other. And that's a lot of the goal of what I'm going to be showing you today. Okay, so with that sort of framework in mind, let's get started, and let's start with Galileo. Okay, so I'm guessing that in this audience, these pictures are probably familiar to many of you. In case they're not, this is Galileo's notebook from 1610, and over here he's making some notes, and down here he's drawing some pictures mixed in with the notes. And the pictures show you his first telescopic observations of Jupiter. So I'm guessing that all of you know that Galileo was the first person to take a telescope and look at astronomical objects, and one of the things that he decided to look at was Jupiter. And he noticed that there were some dots next to Jupiter that he of course thought were stars because other planets were not known to have moons. And he said, these seem to be moving in some odd way, and he's making notes here. And then he cleans up his notes and turns them into what we would now call a time series, and in visualization you would call small multiples. Okay, so these little boxes here are the 7th of January, the 8th, the 10th, it was cloudy on the 9th, the 11th, the 12th, etc. Okay, and he's saying this is Jupiter, and then these other things are I don't know what, but they seem to be moving. It's an interesting story that when the book was eventually published as Sidereus Nuncius, the actual positions of those asterisks that you see there, if you try to reconstruct the orbits of Jupiter from that, you get the wrong answer. And this is a very good example of the limitations of technology for communicating visualization. His hand-drawn notes are far more accurate than that because the printing press couldn't put the little symbols in the right place. So Galileo started us in really this partnership between human cognitive system and visualization and astronomy and astrophysical discovery. And so this is 400 years ago. And so what I want to show you now is, this is great, what Galileo did, but I want to show you what you can do with a modern tool like Worldwide Telescope to try to really understand and explain what Galileo did. And so I'm going to show you some excerpts, some video excerpts from what is actually a very interactive tour that explains Galileo's discovery of Jupiter's moons. And so I'm going to let this play for a minute.
When Galileo published his findings in his famous book, The Starry Messenger, This is what he said about his observations.
On the 7th day of January in the present year 1610, at the first hour of night when I was viewing the heavenly bodies with a telescope, Jupiter presented itself to me. Beside the planet there were 3 starlets, small indeed but very bright. Though I believed them to be among the host of fixed stars, they aroused my curiosity somewhat by appearing to lie in an exact straight line. There were 2 stars on the eastern side and 1 to the west. The most easterly star and the western one appeared larger than the other. I paid no attention to the distances between them and Jupiter, for at the outset I thought them to be fixed stars.
The next night, things got interesting.
Returning to the same investigation on January 8th, led by what, I do not know, I found a very different arrangement. The 3 starlets were now all to the west of Jupiter, closer together and at equal intervals from one another.
This arrangement interested Galileo not only because it was different than the previous night, but also because the points of light around Jupiter did not appear to move in exactly the same way as Jupiter did relative to the visible stars.
Now, I'll show you worldwide telescope several times, but I just want to make a personal note that the way that this tour was made, Pat Udompersert, who I forgot to mention on the first slide, runs the Worldwide Telescope Ambassadors program here, which is an outreach program based on the computer program Worldwide Telescope. And she got to actually, you'll notice that it says there that it's the 7th of January in 1610 under observing time. And so within Worldwide Telescope, you can manipulate the sky to look like it would look at any particular time and then overlay graphics the way that you saw. So this is all, again, made in a program that will come up many times in this talk. But let me just show you a little bit more of that tour.
Galileo understood that if he could have observed Jupiter without interruption by daylight or poor weather, he would have seen this. Today we can see Galileo's correct picture from many perspectives, including a calculated view of Jupiter and its moons as seen from above. These modern images are taken from space. The most important perspective Galileo offered on Jupiter and its moons was actually about the Earth and its moon. In Galileo's day, people had difficulty understanding how the Earth could keep its moon in tow if it orbited the Sun. Newton's theory of gravity was not published until 1687, 77 years after Galileo's first observations of Jupiter. But even without a detailed understanding of gravity, Galileo's results showed that a planet could, in fact, hold on to its...
Okay, so I cut it off there, but you can see that you go from Galileo's visualization of little sketches to a plane of the sky view where the moons are going back and forth to a three-dimensional view explaining why it is that things look like they're going back and forth on the sky. Okay, so that's where we've come in 400 years. But to show you what happened in between, okay, so here's Galileo in 1610, and all sorts of other interesting things happened along the way. This is a plot of the density of important developments in graphics and visualization as a function of time. And I'd love to go into the details, but I'll skip them for you. And instead, I'll just focus on what happened here in the 1800s, and then I'll come back to the present. Okay, so in the 1800s, 2 giants, one of whom, Playfair, who invented what we would call statistical graphics today, and Menard, what a lot of people would call information visualization, was invented by him, lived and worked as engineers and draftsmen and a lot of other things in the 19th century. And the kinds of graphics that they made looked like this. And the reason that this is really important is because the 1800s was the first time when you could mass produce graphics and you could print them in color. Okay? And so these are beautiful color lithographs, they're reproductions of these kind of graphics. For example, when I say Playfair invented statistical graphics, he invented the bar chart. Okay? Somebody had to invent that. He also invented line graphs. Okay? Menard was more of a map-focused person, but you can see these kinds of diagrams that you see now of trade routes and things like that were developed in the middle of the 18th century. Okay, so this was beautiful, and visualization was headed in a very good direction. And then what happened? There was kind of a peak, this sort of golden age of visualization, and then things started going really bad. And why they went really bad is a good question, but let's leave that for another time, and just point out that computers enter science around here. And you may remember that there used to be draftspeople who made graphics for you, and they were really good at it, okay? And they had a certain craftsmanship, a certain ethos and aesthetic that they wanted to apply to the graphics. Computers did not have that. Okay, and computer graphics, computer visualization was very ugly for quite some time. But what's happened recently is that it's become possible to take tools that are made by people who are really good at both sharing information and in a quantitative way and also being very visual, and mash them up. So how many people know what mashup means when it refers to music? A few of you. And how many people knows what mashup means when it refers to software? Roughly the same people. That's very interesting. Okay, so anyway, what it means is if you have a program that can talk to another program or that can plug inside of another program, that you can build on things that other people already made. So the same way that someone invented the bar graph, and then to reuse a bar graph, you just draw a bar graph. It used to be hard if somebody invented some kind of software to reuse their software. It's become much easier to do that. And so what I'm going to show you today is essentially a stack of things. These are worldwide telescopes, something about 3D PDFs, some software called GLUE, something else called C3PO, an ADS all-sky survey. I'm going to show you how these things connect to each other to make kind of a new ecosystem for doing research and in particular visualization. Okay. So how many of you have ever seen one of these in real life? Those who have small children or who really like electronics. Okay, so what that is a box where some of these things are like resistors and capacitors and transistors and propellers, and it's a very modular, literally snap together way to make and experiment with electronic circuits. And so when I say software mashup, think of something like that, okay? But think of tools that go all the way from the most basic thing like a resistor, so Python, to a sophisticated thing like a propeller. Okay, which is some of this other software here. And you can put these things together to make all kinds of different objects with the same tools. And so let me just show you an example of a few pages of examples of what these sort of Web 2.0 mashups in visualization look like. Okay, so this is a program called Plotly. That's an online data visualization program that we're actually using in my Art of Numbers undergraduate course here at Harvard. And then the next few pages are from something called D3 or D3.js, which is a suite of JavaScript tools that can make all these different kinds of plots. And you'll notice that these plots look a little bit nicer than your typical plot in the Astrophysical Journal. And so we could all be using these tools, and hopefully more of you will be using them after today.